Hello everybody, we are the winning team of Roads Challenge from USTC. I'm honored to be here to present our solution. Our presentation will consist of the following 5 parts. The first is an introduction to the Roads Challenge. The focus of the challenge is to develop solutions that can reduce the performance gap between the training side and real-world test scenarios. The challenge is set up with multiple video corruption methods. 2 randomly selected frames of spatial corruption from HMDB 51P are shown here. We can see that the video has serious noise problems or compression problems. The challenge faces the following difficulties. Firstly, the artificially corrupted video dataset is 4 times the size of the original, of which Kinetics 400p reaches 724 GB, which puts a great burden on the inference. Secondly, the dataset is severely corrupted and there are very many types of corruption. Finally, in comparison with images, videos also involve temporal corruption. Facing the above challenges, as seen our overview solution in the figure, we take the transformer as the backbone, adopt the multi-scale sampling strategy to get frames of different scales, and then the spatial corruptions and the data augmentation are performed on these frames to enhance the generalization performance of the model. Finally, the models of different scales are assembled to obtain the final prediction results. For spatial domain robustness, during the data processing, we simulate 20 corruption methods with a 50% probability to be randomly applied on video sampling frames for training, which improves the robustness of the model in the spatial domain. For temporal domain robustness, we believe that due to the powerful global modeling capability of the transformer, increasing the sampling interval not only doesn't affect the modeling of temporal features, but also weakens the effect of temporal corruption. And we innovatively propose a multi-scale sampling strategy by setting different scale to train the model, which can learn different temporal scale features and mitigate the impact of temporal counts on the model. We use transformer as a backbone and experimentally demonstrate that its anti-interference performance is significantly stronger than that of the CNN-based models. Also, we take trade-offs to ensure the consistency of clean samples and disturbed samples in input and output space. And finally, we assemble the multi-scale sampling models to capture video sequence information more comprehensively. To determine the optimal corruption ratio, we conducted experiments using HMDB 51, corrupt videos at different ratios and check its accuracy on HMDB 51P. The results show that the model has the best robustness when the corruption ratio is 50%. After determining the corruption ratio, it is also necessary to determine the severity of corruption. There are 5 kinds of severity levels when performing corruption. We choose 2 and 3 severity levels to conduct experiments on the HMDB 51 dataset. The results show that the model achieves the highest accuracy when the severity level is 2. Thanks to the powerful global modeling capability of the transformer model, we find that appropriately increasing the sampling interval not only doesn't affect the modeling of temporal features, but also weakens the effect of temporal corruption. As shown in the table, for each video we sample 12 frames fixedly, at intervals of 4, 6, 8, 10, and 12 frames respectively, and the top one is gradually increased. Since average number of frames of HMDB 51 is 96, we ensure that frame interval product clip length is near 96 when we perform multi-scale sampling. We successfully sample 6, 7, 8, 10, and 12 frames, and then perform multiple inference results, for example, which effectively improves the robustness of the model. In conclusion, transformer based on transformer's backbone is more robust to sequential data than models of CNN. anti-corruption method with a 50% probability to be randomly applied on video sampling frames for training, which improves the robustness of model in the space.
Hello, we are Yin Yang team. Our members are Li Tingliu, Shen Shendu, Zhongmen Cai, Shuoping Yang, and we are honored to have the opportunity to participate in this presentation to introduce our technical solution. It mainly includes 4 parts: background, methodology, experiment, and conclusion. Firstly, is the background. Generally, there are great differences between the training set and the actual test setting. As shown in the training set, the training data is generally clear. However, as shown in the real-world data, sometimes data contains more noise due to corruptions, camera-related perturbations, comprehension. Therefore, the challenge is to develop solutions to improve the robustness of the model and narrow gap between the training set and actual test setting. The DOS 2022 provides 3 datasets for model accuracy validation: HMDB 51P, UCF 101P, and Kinetics 400P, which are all corrupted and perturbed. Then, we will present our approach. This is the overall pipeline. Raw frames are first extracted from provided raw videos. These frames then perform data augmentation between spatially and temporally. The processed frames are then sampled using a constant sampling technique and passed through the R2+1 D-BERT network and swing transformer network. Finally, the outputs of the two networks are assembled, which produce the final classification. We selected an appreciate architecture for the video domain called R2+1 D-BERT. This network is based on the R2+1D model, and the TGAP layer is then replaced by BERT to better utilize temporal information. Also, we set the initial point as the pre-trained parameters trained on Kinetics 400 datasets. By observing the dataset, we believe that adding different kinds of noise to the training data properly drop out some pixels of the sample, occurring, scaling, and flipping the sample data can greatly improve the robustness of the model. The nice spatial data augmentation visualizations we used are shown below. Like the above method, we also use data augmentation in the temporal dimension. In order to make the model run the temporal dimension features more effectively, our data augmentation on temporal dimension includes randomly filling frames, playing in reverse order, video acceleration, and video slowdown, etc. The processed videos can be seen in the following clips. Then we introduce our experiment. We conducted ablation experiments on the network structure. The first group used R2+1D TGAP network. The second group used the efficient net BERT network, and the third group used the R2+1D BERT. The experimental results showed that R2+1D BERT had the best performance on HMDB 51P dataset. We choose R2+1 D-BERT as the experimental model, and the data augmentation methods in spatial dimensions are used on the sampled video frames. We divide the data augmentation of 9 spatial dimensions into 3 groups and select one group each time for the experiment. Finally, we conduct the data augmentation of 9 spatial dimensions together. Experiments show that the data augmentation strategy improves the accuracy by about 9.58% on HMDB 51 and about 7.34% on UCF 101. We have also done some experiments related to data augmentation in the temporal dimension. We divided 4 augmentations in the temporal dimension into 3 groups, and each time we selected one group for the experiment. Finally, we combined the 3 groups and performed the experiment. Experiments shows that the strategy can improve the accuracy of HMDB 51 by about 4.31%. Finally is the conclusion part. Through the methods and strategies introduced above, our accuracy of HMDB 51P, UCF 101P, and kinetics 400P datasets and reached 92.54%, 92.56%, and 70.55% respectively, and we won the second place. Thank you.
Hi, my name is Keval Doshi and I'm from the Secure and Intelligent Systems Lab at the University of South Florida. Today, I will be presenting our work on semantic video transformer for robust action recognition. Video action recognition has attracted significant research attention over the past several years. Although adversarial effects and robustness in image classification models have been heavily investigated, robustness of action recognition models to natural or adversarial perturbations remain largely unexplored. Moreover, even though transformer-based approaches have shown great promise on various vision tasks, they have yet to be evaluated in terms of their robustness. In this work, we propose a semantic video transformer for action recognition model, which we call SEVITAR, and we show that this model is able to map visual features obtained from the visual transformer to a more robust visual semantic representation. The proposed approach is as follows. The input video is sent through a multi-head self-attention transformer model, which consists of divided space-time attention. This transformer model outputs visual features which are then sent through a semantic MLP. The semantic MLP tries to map the visual features to a semantic space by minimizing the mean square error between the output and the semantic embedding of the class labels. These semantic features are then combined with the visual features and sent through a classification MLP. The classification MLP is trained end to end to finally classify the input video. Here we show the TSNE visualization of the I3D features and transformer features extracted from the UCF 101 dataset. Each point represents a video and various classes are represented with different colors. We see that the features learned by the proposed transformer model on the right are semantically more separable than the I3D features on the left. The UCF 101, HMDB 51 and kinetics datasets are three publicly available benchmark datasets that have been commonly used in the majority of recent studies to evaluate action recognition performance. To evaluate the performance of the proposed approach in terms of robustness, we use the ROSE challenge dataset, which consists of perturbations such as spatial, temporal, camera related and compression corruptions added to the benchmark datasets. A sample set of the perturbations are shown here. The introduced perturbations make it significantly more difficult to recognize activities. Moreover, the intensity of the perturbation is different in each video. In terms of the results, on the Kinetics 400 dataset, we were able to achieve 70.49 and were placed 4th. On the HMDB 51 dataset, we were able to achieve 78.92 and were placed 3rd. On UCF 101, we achieved 89.35 and were placed 3rd again. Thank you.
Hello everyone, I'm Citao Gao from Wuhan University. I'm glad to be here to give a short report about a solution to Romanes in sequential data challenge. I'm going to share you our work from the following three parts. Firstly, analyzing the data sets, and then introduce our solutions, and finally conclude the results. Okay, let's get to the first part. We need to evaluate our approach on three datasets, of which HMDB51 and UCF101 are relatively small datasets with 51 and 101 categories, respectively, and a small number of videos. And Kinetics 400 has a large amount of data and more categories, with 400 action categories. The resolution of the videos in these datasets also varies. And our task is that our model can make a correct category judgment for the videos with perturbations. We randomly selected some videos from the test set and counted the types of perturbation applied in the test sets, which were divided into 11 kinds of perturbation. For example, like salt and pepper noise, blur, jitter, and so on. We found that the most proportion of them are some noise additions, frame repetition, and frame missing, and other timing perturbation account for less. After comprehensive consideration, we decided to perform single-frame wavelet denoising before feature extraction. And the next part is our solution. For the frameworks, we try many models such as swing transformer, TSM non-local, slow-fast, TANet, and transformer, and among which the swing transformer gives us a surprise. And our experimental setup for the training phase is shown below. We choose AdamW as optimizer and warm-up is applied. The weight decay equals 0.05, learning weight equals to 10 to the power of -3, batch size is 64, and we also applied stochastic depth and set the ratio 0.4. The temporal window size is 16. For the data augmentation, we firstly denoise the video by frame and then used random resize curve to resize the image to 224 times 224. The random erasing is also adopted. And finally, for boosting the model performance, we assemble all the models for accurate results. And the final part is the conclusion of our results. Due to resource and time constraints, we mainly consider the dataset Kinetics 400 for our experiments, and our solution achieves the best on the Kinetics 100 mini-test set and the second on the full set. And our experimental procedure and results show that swing transformer is an excellent network for action recognition. In addition, a suitable preprocessing process somewhat helps to enhance the input data. And finally, assembly of model is a necessary means for accurate results. And that is all my reports. Thank you for listening.